Okay, welcome to Fractals Part 2. Let me get a share screen going here. So I mentioned the Mandelbrot set, Benoit Mandelbrot, who discovered the Mandelbrot set in 1979 while playing at IBM. I showed you these examples the other day. The Mandelbrot set, you zoom into it, and you zoom into it, and you zoom into it, and this recurring structure that looks the same at whatever scale you look at it continues to appear. I'm not going to show you the YouTube videos. There are a number of them linked in this document that you should really go and look at. But the Mandelbrot set is an example of complexity that emerges from very simple rules. Game of life is another example. We might look at that later. The idea here is that we treat the coordinates of the screen as the real and imaginary parts of a complex number. You know, complex numbers have a real part, x, and they have an imaginary part, y, where I is this magic number, I squared is -1. That's, I is the definition of the square root of -1. So the whole Mandelbrot set is generated with this simple recursion formula. We start off with a C that is some point on our computer screen where X is the real and Y is the imaginary, and with a Z0 that is at the origin here. And then we iterate. We square the Z, add C to it, and that gives us Z plus 1. So 0, 0 squared is going to be 0. So Z1 will be C. And I think these actually should be labeled Z1, Z2, Z3, and so forth. So as we do this iteration, this complex number will move around the complex plane shown by our computer screen. So as we magnitude, one of two things, as we iterate, one of two things happens. The magnitude of Z, that is the distance from the origin in the complex plane, blows up. It moves away from the 0, 0 spot. Or it remains finite. And if for a given C, a position on our computer screen, if this magnitude of Z remains finite, then C is said to be a member of the Mandelbrot set. There are lots of different quantities that we can display here. For instance, we might display the magnitude of the number after it has settled down, whatever that means, iterated for some maximum of iterations, and it hasn't blown up yet. This would correspond to the numbers in the Mandelbrot set. So for each of these, the grayscale indicates the magnitude of the number that you reach after you iterate. And these black ones, of course, have all blown up. They got too big and blew up, went off to infinity. But these all stayed finite. This funny shaped Mandelbrot set, those remained finite inside that strange thing. I think the origin is right about here, the 0, 0 spot. So grayscale is not very interesting. We might color it with an indexed color map. So we break our range 0 to 1 up into different RGB color values. We've got some little function for reading a color map. We can read these in from a file, colormap.cpt, assign the color map different red, green, and blue values scaled with 255 there. We need a function to find a color in the color map. Hunt is an example of a function. It's it divides the interval in two each time. So it halves the interval that it's searching in. If it's larger than, it discards the other half. If it's smaller than, it discards the upper half. Interpolate is a function that is going to mix the colors together. So we have our two different color map values, and we're kind of blending them together. So that interpolates the colors between those. The other thing we could display is how many iterations take place before the magnitude exceeds some specific value. In this case, 4. Any time that it gets more than 4 away from the origin, it goes on to blow up. So we could color all these outer spots, the spots that are not in the Mandelbrot set, according to how rapidly they retreat from the origin. And the best of both worlds, we display the n value inside and the iteration count outside. So we get this pretty color Mandelbrot set with all kinds of coloration, and it's interesting. And the different zooms you might look at, they all use different color maps, different ways of displaying them. And here again are another list of fabulous deep zooms into the Mandelbrot set that will waste time for you. So the computational load of the Mandelbrot set is this iteration. That's what we're doing that is computationally expensive. For each pixel on our screen, we have to iterate into the depth of the Mandelbrot set to see whether it blows up or whether it remains finite. And each point is independent. Doesn't matter. They don't interact with each other. Each pixel starts off a different spot, and it goes wherever it goes, independently of its neighbors. And so this is a perfect kind of computation to do in the GPU, which is really good at independent operations. The CPU is going to handle zoom, pan, so forth, and it'll generate a checkerboard of vertices that will pass to the GPU. Whenever we change the zoom or pan, we'll reformat the checkerboard and pass that to the GPU. There are other ways of doing it. So if we begin with our rectangle at its 4 corners, these are 4 corners in the complex plane. They're going to map to our screen, min, max, y min, and y max. There should be a y there. The zoom the zoom button that we have, some button that's labeled zoom, is going to figure out where the center. It's going to figure the width. It's going to reset the min and max corners. It's going to load all these points, set points. It's going to flatten them, send it to the GPU. Set points is just going to go through that checkerboard. I equal 0 to width, j equals 0 to width. The x value and the y value. This just goes along the checkerboard and push those vec4s into our array. The render function is really simple, since all it does is display the screen. It draws the arrays, it draws them as points, so there's nothing fancy there. We have a orthogonal projection here, since we're just looking at a flat map. Mainly what it does is it displays how deep we are and what the point separation is. So that's this display text items that handles the UI. This is a kind of an automatic setup of text where you just cut and paste things in, and however many items you need, and it's all set up. Here's the index color map to be loaded. And here are the intervals for the color map. So these are the different RGB values. And these are the intervals at which each of those colors occurs. Load and send them to the GPU. This is only done once. The fragment shader is really simple. The fragment shader is going to merely catch the varying color. Because the vertex shader is where all the work gets done. The main is also fairly simple. All it does is take the X and Y out of our vertex position, the position of those checkerboard points on our screen, and it runs the iteration that returns a color, and we multiply the V position by the projection matrix for the GL position. Iterate is the workhorse here. It does the complex arithmetic with a little routine CMULT that I've written. It assigns a color by interpolating, and that color is based on whether it has blown up or not. So here's our iteration loop up to some maximum number of iterations. Here's our recursion relation. CMULT is the squaring of the Z. There's the C. C, notice, comes out of the X and Y positions of the iterate. Iterate is passing at the X and Y positions of our V position. These are the points on the screen, the vertices. I'm calculating a difference between them to see if they settle down. If length diff is less than 10 to the -5 here, I'm going to break. Also, if length of Z0, the length of our vector, is greater than 4, I'm also going to break. And I'm keeping track of the length here. That's my magnitude. And if it's greater than 1, that is, it's blown up, then I'm going to use the count, the iteration count for coloring it, divided by max iteration. So that's going to be 0 to 1. And otherwise, I'm still using the magnitude of the number here that was calculated in the iteration loop. I'll do the interpolation, return that color, that temp color, a vec4 color that appeared here. That was the color, the varying color. Where's varying color that gets passed on to the shader that gets displayed, and that's all there is to that. The complex multiplication, the imaginary parts, the IA times IB gives me an I squared, which is a -1, and the other, the imaginary terms, AYBX and AXBY, remain imaginary. So this is the real part input, and this is the real part output, and the imaginary part output. So Interpolate, I think I showed you that a minute ago, locates the interval in the index color map, uses this hunt function. It also uses the GLSL mix function to kind of combine colors. So here I'm mixing these two colors according to their position within the interval. And the hunt function, this is that midpoint method that discards half the search space at each step. A fundamental limitation that you'll see of doing this is that GPUs have only single precision numbers. Some of them are beginning to have double, but generally single precision is all you get. As a result, as the step between our vertex position approaches 10 to the minus sixth, the limit of precision of our single precision numbers in the GPU, the checkerboard begins to show some banding. Those deep zooms that you can watch on the web do really fancy tricks to obtain high precision that is way beyond what we can do. So let me show you my version of this, or the version that that we generate here. Where's Mandelbrot? So this is exactly that code that I just showed you there. So here's the Mandelbrot set to start with. I can zoom in on this. Everything is so slow when one is using, well, let me go to a preset. This starts off deep, if it ever catches up. So this starts off deep, and I'll zoom now back out. You could begin to see the banding there that's disappearing here as I zoom back out. We'll find ourselves at a different place. This is tedious. So I guess you get the idea of what we can do with this. I'm going to post this program for you to play with. And I'm going to stop the share here and back to the main world. And I'm going to end the lecture at this point. So that's the Mandelbrot set, a classic computer science thing. And I'm going to stop recording. I'll see you all in class. Bye.